This
of
conference
University
will
of
now be
Birmingham
recorded.
students building track at the who are installing track at the Ecclesbourne Valley Railway, which is an annual activity, and it's a real live event. It's not virtual, it actually exists. So I thought that would be a nice starting point. Then the next slide is basically just an introduction to myself. I work at the Birmingham Centre for Railway Research and Education at the University of Birmingham, and that's for those people who are not so familiar with the UK or geography, is in Birmingham and a suburb called Edgbaston, which will soon have a tram. And my areas of interest are rail systems engineering, control systems, signalling, and engineering education. So what I'm going to try and do in this session is to talk about two different approaches to high-speed railway design and operations. The picture you see is from another rail event about 3 years ago, Rail Live at Long Marston, and we hope that this will be run this autumn in September. Okay, so I'm going to talk about second generation high-speed rail in Europe versus Central Japan's railways lean approach. It's not going to be a lot of history, just a small amount at the beginning. So maybe if you think back to the Rainhill Trials in 1829, they were about speed, and that was a very important point because they wanted to achieve a short journey time between Liverpool and Manchester. But more than anything else, it was about reliable performance. And the locomotive in the front is Stephenson Rockets, which was running reliably for an hour, and then in the background there are some locomotives which either didn't run at all or ran for a very short period of time. So the rocket achieved 48 kilometers per hour, which in 1829 was an amazing achievement. And it was not bettered for a while. And of course, we are keen to see more things today. What this brought was that railways could shrink time and space. It became possible to have leisure travel because the time was sufficiently short that somebody could do that even if they were working. Food didn't perish anymore, so people in cities could actually eat more healthily, and they changed labor markets. And as we can see at the present moment, the railways are still supporting the labor market, and it's essential that they do so. Here is a diagram from China, which shows the Chinese high-speed railway network and also this feature of time and space shrinkage. The idea is that there are a high-speed rail network which brings everything close to Beijing, because Beijing is actually not in the center, it's actually to the east and northeast of China. And that means in order to tie the country together, high-speed rail is a key method to do so. Now, real high speed, in my mind, started in the early years of the 19th century, 20th century, with the trials at Zossen-Marienfelde Military Railway by two German companies, AEG and Siemens Halske. Those trials were with AC 3-phase, which was a bit cumbersome, but running at 200 kilometers per hour reliably with no smoke, no noise was a big achievement. This is the sort of history of high-speed rail. As you can see, in about 1909, we moved from steam traction to electric traction. And as we moved on, further on, the speeds increased and increased. And the sort of types of speed we've got is high-speed rail, very high-speed rail, and what I call silly speed rail. Silly speed rail is something which we do for fun. It's not something which we do because it's got a commercial benefit. And that's, of course, silly speed rail, the fastest wheel rail train anywhere in the world. And it reached 160 meters per second. People tend to wonder why the 574.8 kilometer speed was so highly advertised. Well, it's really just because it's 160 meters per second. So roughly 1.5 times what Mr. Bolt does in 10 seconds. So pretty cool. They were not all high-speed rail systems were a success. This was the Aero train in France. The infrastructure is still there in fields around Orléans. It wasn't really a big success because the capacity was too small and the noise was just stupendous. So I'm now wanting to go over to what I'm actually advertised to talk about, which is a high-speed rail case study, which I'm doing with many thanks to Central Japan Railway, who invited me for a 2-week visit in 2012, and the Association of Train Operating Companies who organized that visit. So I'm going to first of all talk a little bit about conventional thinking of high-speed rail systems, then why it's so successful in Japan, and then a little bit about this visit I made to Japan. Why? Well, I had read a lot of things about Japan as part of my engineering career. I had read a lot about Japan's railways and the Shinkansen. And I have to admit, I thought I would have learned nothing at all going to Japan, but it would be a nice jolly. But it wasn't. I did understand a hell of a lot of things. And I also brought back Daisuke from Japan, who became an excellent doctoral student at Birmingham. And he's actually going to feature in this talk. So what I would call agreed, and it's inverted commas because not everybody agrees with this, high-speed rail principles are about minimizing the journey time by operating continuously at high speed, minimizing the journey time by reducing the number of stops and the necessary slowdown and speed up, minimize the journey time by reducing the duration of dwells at stations, optimize the station and station design principles, and use the best technology that money can buy. Now, you might sort of have a feeling that I don't agree with all of this, and this is really what this talk is about. So high performance infrastructure is essential for high-speed rail. We all agree on that. And the high-speed railways should therefore have high-speed turnouts where you can go at very high speed and in reverse direction going as high as possible. They need long overtaking and stopping loops to give the best performance. So what I've drawn here is a top-of-the-range European high-speed rail station. It bears some very significant similarities to what's planned for the station at Birmingham Interchange. And what you can see is that the train starts to brake about 6,000 meters from the platform end. So that's the end of the platform where the train will come to a stop. We have a junction where the train can diverge at 230 kilometers per hour, and then another one where it diverts at 95 kilometers per hour, ends up in the platform, and then of course will go out again. Now, that's a lot of space, it's a lot of infrastructure, and it's some very complex and safety critical infrastructure with the points. So if you look at those two sets of points, I've had a drawing made by Andy Phone, who very kindly produced my layouts here. So a 95 kilometer turnout near the station is about 80 meters long, or back to tangent tracks about 160 meter long. The 240 kilometer per hour layout requires some 220 meters to the crossover center and 440 meters for the whole length of the arrangement. And that's just looking down on a bit of the high-speed line between London and the Channel, and you can see that high-speed points are very long and therefore very complex. This is an example from Turkey, And anybody self-respecting who wants to build a high-speed railway will, of course, choose that type of infrastructure. This is relatively high speed. It's 200 kilometers per hour on the diverging track in Switzerland. And if you count, you can find that there are about 10 point machines, point operating mechanisms in this picture. The best kit that money can buy. That's the typical Swiss attitude. So I'll now compare this a bit with Japan. This picture here is essential because it shows Mount Fuji from the hotel window where I was staying in Tokyo. It's a very, very great rarity to see Mount Fuji. Usually it's covered in cloud and pollution. So I was extremely lucky at that time. So Japan and Korea by night is a first introduction which we probably need to know about. So we've got here the densely populated areas in Japan and in South Korea, and a bit of North Korea where there's not an awful lot to see. So Honshu is the main island of Japan. It's where most of the population lives. Then Hokkaido is in the north and Kyushu is in the southwest. And both of those are far less populated and far. Honshu has 105 million inhabitants out of 126 for the whole of Japan. These are the numbers from about 4 years ago. Honshu has got most of the landmass of Japan, and it's got a lot of big cities. And if you look a bit further down, Hokkaido Island has got a population is smaller than that of London. And so it is very big, but certainly not very populated. Most of the commercial activity in Japan is centered on the area between Tokyo and Osaka. It's about 23% of the total land area, 60% of the population, and 64% of the GDP. So it's a high intensity corridor. And you can see that here in the picture. The gray line which you see is the planned maglev line between Tokyo, Nagoya, and Osaka, which is currently under construction. Now, it's always useful to have a little look at the distances involved. So here I've entered the main cities, Hiroshima, Osaka, Nagoya, Tokyo, and a circle around Tokyo with a radius of 300 kilometers. And what we can see is that most of the cities, if not all, are outside that radius. So there's a distance where speed really, really matters. So that's where I tend to sort of draw the line, whether it's worth building a high-speed railway or not. And that's the situation. And the Tokyo Osaka Shinkansen was built for the Olympics in 1964. And it was a very deliberate choice to build that in standard gauge rather than Cape gauge, which is what the existing railway was like in Japan. In order to avoid people coming onto this line with freight trains, people coming onto this line with commuter trains, basically they wanted to have a high-speed line with electric multiple units from the word go. It opened at 200 kilometers per hour, and it's been accident-free ever since due to traffic separation and railway control systems. The system was so successful that it's now over 2,400 kilometers long, and more bits are being built all the time. One has to say, though, that most of the Shinkansen network is actually not profitable. The really profitable bit is the first one from Tokyo and Osaka, and a little bit on each side, but most of the rest is subsidized by suburban services. So Just a picture which shows the distribution of the different railway companies in Japan. So starting at the bottom left-hand corner, you've got the Kyushu Shinkansen, you've got the Sanyo Shinkansen, which is West Japan, you've got the Tokaido, you've got East Japan Railway, which runs the Tohoku and the Joetsu and Hokuriku, and then you've got the Hokkaido Shinkansen, which is currently quite short. But all of this is being extended as time goes by. And again, our distances, they are very, very important for making high-speed rail viable and sensible. This is a picture from Tokyo, from Kumamoto, just to show what the trains look like and how inviting they are. Now, when I looked down from the hotel, I was shocked. If you look at this situation here, it looks like a 1940s or 1950s track layout. And if we look here, a set of points which is 50 meters long is in my book, and was at that time in my book, not a high-speed point. It was just old. And I thought, why have I gone to Japan to spend 2 weeks learning about 1950s technology? I was completely wrong, and I have to admit to that. So the Japanese approach here, in comparison with a 95 kilometer set of points and the 230 kilometer point, looks like this. It's a 70 kilometer per hour point. And I just couldn't believe that. Why would you have such short and inadequate points on a high-speed rail network? Well, I learned very quickly that this was actually by design, and it was extremely beneficial. So the first thing you can see here is, if you work on that assumption, then your braking starts at 4,800 meters rather than nearly 6,000 meters. The trains slow down quite quickly. They get into the station at relatively low speed and come to a standstill. And here I've drawn some braking curves and also some train following curves. And I think the PWI likes fairly technical stuff, so I hope you can follow this. So the curve which slopes down to the right, that's the braking curve for a European train on a European type infrastructure, and a braking curve for a Japanese train. You can see that the Japanese train starts braking quite a lot later. It breaks down to a lower speed and covers the last bit of distance into the station at fairly low speed, well, 70 kilometers per hour, and then comes to a standstill. The European train goes through the junction at 95 and then also slows down. Now, that's very advantageous. Now, people will of course say, but that reduces your capacity because the trains are not following each other as closely as they could. So which is why I've drawn the curve for the European train slowing down and the next train which passes behind it. So the European train, the next one, is probably about 3 or 4 seconds earlier than the next Japanese train. But remember, you've saved a huge amount of infrastructure. And I'm now showing the trains and the platforms. And we are now going to have a look in a little bit more detail at the situation. So you've got your trains, 2 trains slowing down, the Japanese train slowing to a lower speed and then coming to a standstill with a higher braking rate than the European train. This is what's called the turnout clearing distance. So that means when the train has passed the turnout, it can start to change its speed. And for the Japanese train, that is quite a lot later, and therefore the next train can follow after it. So why is this the case? Well, when we actually build a railway, then you can look at 3 items. You can look at services and timetable, you can look at the rolling stock, and you can look at the infrastructure. This is a diagram which Swiss Railways developed, and I think it's quite a useful one. You go around this circle, improving and improving as you need more performance. Now, the first stage is not shown, and that's identifying the demand, the quantity, the journey time required, etc., what competitors you have. So in Japan, that was the aircraft sector, which was completely congested, and the roads, which were absolutely full. So there was no problem about demand in central Japan when the railway was being built. So what the Japanese do is to first of all design the best rolling stock that they can with high amounts of power and high number of powered axles. Then they design the infrastructure, and then they define the timetable. In Europe, very often we start with the infrastructure, then we define a timetable, and then we try to find trains which are able to both work to the timetable and are able to climb the gradients which you have provided with the infrastructure. It's, to my mind, a suboptimal approach. So designing the best possible rolling stock is first of all about building it light. A Shinkansen train N700 weighs 730 tons. It's got lots of seats. It's got most of the axles powered, so 56 out of 64. The latest version has got 64 out of 64 powered, and a total of about 17.1 megawatts. So it reaches 300 kilometers per hour in just 11 kilometers. And what's even more important, it allows electric braking down to 15 to 20 kilometers per hour. One of the experiences I had in Japan was a bit embarrassing because we were visiting the rail research establishment of Central Japan Railways. And in the entrance, they had 3 traction motors displayed, which had all been developed at this facility. A small one, a medium-sized one, and a big one. And I looked at the labels, and the big one was the most recent. So in the first meeting, I said, "Are you sure that these labels are correct?" And they said, "What labels?" "Well, the biggest machine is the most modern. Isn't that sort of not what we would expect?" They said, "Yes, of course it's what we would expect, because we are trying to regen to as low a speed as we can from as high a speed as we can. And so therefore we need big traction motors which can absorb the heat, which can absorb the electrical currents which are necessary." So I had learned something else. And then you've got the design of the rolling stock that copes with this job in hand. If we look at the Pendolino, which runs between London and Birmingham, the 9-car version weighs 460 tons. It offers 480 seats. So the ratio is rather not as good as for an N700. An N700 has about half a ton per passenger, and the Pendolino about a ton. So that's quite a difference. And the power is relatively limited because only 14 out of the 36 axles are powered. So it takes a lot more time to reach a high speed. And when you brake, you need to use mechanical brakes at high speed in order to get rid of the energy in a reasonable amount of time and distance. So high acceleration and braking rates is what allows you to train your train in a completely different way to the way in which Western high-speed rail designers choose to do. And that's just a nice picture because you have to have nice pictures occasionally. So because you've got such short distances to brake, your dwelling tracks at the stations and your stopping distances are small. You can use short turnouts with a very straightforward, cheap S&C. You can have steep gradients and tight curves because you can slow down if necessary. You have a high integrity railway control system And an interesting point about Japan is that they don't provide bidirectional signaling, because work is done in 4 or 5 hours during the night, and they don't use bidirectional signaling because it adds complexity and it adds cost. There is an ATP functionality, but most of the time the drivers do the clever stuff. It's just running the train at constant speed. And but when you approach stations in order to get the best out of the regen braking, once the driver selects braking, it stops the train automatically. Very simple track construction. And as I said, they use a maintenance window each night to improve the situation. And that's just for interest. A typical station, an intermediate station in Mishima, tight tracks. The fast line goes on the right-hand side, and the stopping track has got a very tight turnout. So one thing which is also important is the generalized cost, or the generalized journey time. It's comparable to road transport, but it's much shorter. Everybody sits. There are stations in all major towns and cities. Now that's an interesting point, because Tokyo to Osaka is about 520 kilometers, and there are a lot of stations. There are actually 16, of which 14 are intermediate. So roughly a station every 35 kilometers, which is not what we are used to in the West. It's something which is very beneficial, though, for your corporate relations. It's very beneficial for your traffic, and it's very, very beneficial for the performance of the economy. Of course, the trains are also quite on time. So this is just the three types of trains which run on the Tokyo to Osaka line. The fastest train takes 2.5 hours. The second fast about 3, and the slowest train takes about 4 hours. Now, people tend to jump on a Kodama at one of the small stations, and then they change to either Hikari or a Nozomi at the next interchange where this is possible. So it's an optimized situation, and thanks to the design of the stations, Hikaris can overtake Kodamas, and Nozomis can overtake Hikaris without causing any delays to each other. So, of course, they're building a maglev line, and the interesting point about that is, prior to COVID-19, it was fully expected that this would be built with private money, basically with the profit of the conventional railway between Tokyo and Osaka, because the traffic is so huge. Now, I think in future it will probably not be possible to fund it from that source, so the government will probably have to step in. So the high ratio of motor axles gives good acceleration and braking. You get a lot of electric braking, regen braking. The small size of the turnouts means you don't need swing nose crossings. You need it's low complexity. You can change one in a 5-hour maintenance window, so you don't need to shut the railway down in order to do so. And it's a simple and safe system. The low technology also means that flexible maintenance can be undertaken. So just as a reminder, this is what it looks like, and this is why it's quite a lot different from other places. So this is a sort of general overview on what I learned when I went to Japan. But Taisuke Hasegawa, whom I just mentioned, he came from Central Japan Railway Company, and he spent 2 years in Birmingham and then another year in Japan writing his PhD about a lean approach to high-speed rail. And it's just sort of, it's imagining WizzAir on rail. Everybody does their own stuff, and the plane spends as little time on the ground as possible. And so the lean concepts which Daisuke looked at was, one of all them was continuous improvement, just-in-time production, so you don't keep things in store, looking at which activities added value and which didn't, what the value streams were, and one of the concepts which was developed in Japan and exported to a lot of the motor industry is single-minute exchange of dies. And for the analysis, he used something called the Taguchi approach. So a value stream map for a passenger journey from London to Birmingham is 10 minutes walking to the station. It might actually be more. Queue for a ticket purchase. May come to that in a second. Walk to the gate, have to check the ticket, walk to a platform, board the train, ride the train, get off, and walk to your destination. And go through the ticket gates, and there might be a little queue there. So this is a 60-minute journey time, and that gives you a ratio of the, and I can't see that because something covers my display here. Gives you a ratio between value added time and non-value added time, which is okay. But of course, there are bits of the journey which you'd rather not do, so that's the non-value adding bits. Now, if you change the journey time to 50 minutes, you get a total journey of 95 minutes. The value adding time has gone down a little bit, which sounds strange, but yes, because you're not actually spending as much time on the train, whereas the other things stay the same. So the ratio becomes worse. And if you reduce the speed further from 50 minutes to 40 minutes, the ratio becomes yet more unpleasant. So what you need to do is you need to eliminate things which are non-value adding. And you can, of course, do that by buying your ticket on the internet. The other activities remain, and you have now boosted your non-value, so your value added to non-value added ratio, which is good. So that's your non-value adding time. The second element is just-in-time production. So if we look at conventional operation, you've got 2 hours to paint the product, 30 minutes to bring it to the assembly line, the end of the assembly line, and an hour to assemble. And finally, it spends a day in the warehouse, which is not good. So transport times is basically not useful time. So if we can eliminate that, then your system improves significantly. So occupying a platform is actually an activity like that. So you provide access to a train. That's the role of the platform. It needs to unload and load people. It is used to turn around the train. And we do need to try and increase the efficiency of the train use. We shouldn't spend the train staying at the station for a long time, because each train which is at the station requires its own. So if we increase the efficiency, then we need to make sure that we minimize the use of platforms. Something is going a bit slow here. Yes. So if we go on to some what's called value stream mapping, so actually looking at what things deliver good parts and what things don't. So I've mapped here the arrival of a train at the station, the departure of the train at the station, and those two activities are good. They're part of what the passenger wants. Boarding and alighting is inevitable, so that's also a value-adding activity. What's not value-adding is what the train does while it's sitting in the platform. So if we look at the value-adding steps here, if we can compress the time spent in the platform, then we are actually improving the situation, because if you look at the large number of trains, if there are 4 trains operating and 3 of them standing in the platform at the same time, you need space. and they're not doing anything. They're not earning you money. They are not doing anything at all. So if we can do that, shorten that period of time where the train spans in the platform without actually benefiting anybody, then your journey can be at the same speed. It reaches the station earlier, it leaves the station later, and it leaves the station earlier. Now that reduces the number of trains you require, and it uses less non-value adding activities at the same time. So instead of 4 platforms, you can now live with 3. Now, what do you do? Well, you can do 2 things. You can use fewer trains and keep them running at the same speed, or you can run the trains a little bit slower. Now, what's the advantage of that? Well, it allows you to get some more reliability potentially. It allows you to reduce energy cost. So instead of increasing the utilization of trains, we can use it for other purposes. In Britain, 49% of trains arrive early. This is a statistic of about 3 or 4 years ago. No, actually, it's 2010. But trains were operating a lot of them were operating early, which is of course not good because they occupy platforms early, they use too much energy, and it's only the trains which arrive late within the allowed period which are actually the most beneficial for the system. Now, we looked at the benefits of running trains at a lower speed. So TESSEI looked at a limit of 200 kilometers per hour up to 360 kilometers per hour, and that gives you the profiles which you can see here. Now, there's a significant dip in the speed about a third of the way towards Birmingham, and that's because you've got steep hills, and then there's some further dips where the trains have to go up. Remember, the planned trains for the HS2 are not top performing trains. They are the trains which can just about make their journey. If you look at that in terms of energy use and journey time, then what I've drawn here in blue is the journey time, and in red is the energy. And if we go at 300 kilometers per hour, we compared to 360, we increase our journey time by 3 minutes, and more importantly, we reduce our energy cost by 12%. Now that sounds like quite a good deal, but the 11.7% reduction also translates into a lower power requirement. So the cost of the infrastructure becomes lower, the cost of the electricity supply becomes lower. So operating at a lower speed can have very significant benefits. It does mean that your trains do the journey in a different time, but it's not a big issue. So this is actually very importantly tied in with capacity. If you look at my 3 curves, the bottom curve is for a 2-aspect signaling system, then a 3-aspect and a 4-aspect. And as you can see, there is an optimum speed of about 70 kilometers per hour, where the trains get the best, where you get the best capacity. If you go too fast, the capacity drops. And once you get to 300 or 350 kilometers, your capacity drop is very significant. So this classical signaling, if I now add in some of the more esoteric systems, I've got ETCS, which is the black line. Level 2 gives you a little bit more than 4-aspect signaling. ETCS level 2 for a very long train like we would have on HS2 reduces the capacity significantly, particularly when we go to high speeds. Level 3 brings us back some of that capacity, but it's not hugely beneficial because again it drops off at higher speeds. So this is the benefit of having a lower speed and using your infrastructure optimally. Now, the final element is what's called SMED, single minute exchange of dies. This is from metal forming. If you want to create the hood of a car, it goes into a press. The press pushes the metal down and creates the shape. Now, when you want to go from one type of car to another, you need to change the die which does this job. So historically, it's always been done that you stop your production, you remove the old die, you set the new die, you heat the new die, and then you restart production. And that's a fairly slow process because heating the new die can take an hour. So this part here is going to take you a long time. So single minute exchange of dies changes this by heating the new die before you actually start the process, remove the old die, set the new die, and run again. It can literally be done in a minute rather than in an hour. So what we call this is an external activity. So anything which is internal has to be done in sequence. Anything which is external can be done in parallel. So when we do a train turnaround activity, something similar happens. The train arrives, people get off, it's handed over to the cleaning staff. They check things, toilets are clean, tables are wiped, rubbish is collected, people get back on, and the train leaves. And the efficiency of those three operations, toilet cleaning, wiping table, and collecting rubbish, determines your turnaround. So these are all internal activities. Now, if we collect the rubbish while the train is moving, we take one of these activities out and it becomes an external activity. This sounds like a sort of, well, no-brainer really, but it isn't. It makes a huge difference. This is a cleaning crew being briefed before entering a Shinkansen train for cleaning, and they are fantastic. They clean a complete 440-meter long train in just 12 minutes. So from the point passengers are out until the passengers come back in, it's 12 minutes, which is fantastic. So I imagined, I looked at the situation which Virgin and now Avanti West Coast have. They do the job in a different way. So comparing the TESSEI group on the right-hand side with an Avanti West Coast approach, both have a turnaround time of 12 minutes, which is Avanti actually achieves when there are delays, about same number of seats. The cleaning time is 7 minutes, but the number of cleaners you need is very different. So on an imaginary Class 390 18-car train, you would need 11 members of staff using the Avanti approach, and TESSEI needs 44 people to do the job. Now, the big difference is the onboard cleaners. The onboard cleaners permanently walk through the train. They clean things, they keep the tables clean, they collect rubbish. And so this one lady here is worth roughly 20 Japanese people, which sounds hard to imagine, but she does work very efficiently and she does the job while the train is moving. So if you have the last element in the chain, which is the optimization of the Terminus operation, the plan for HS2 is to have 11 platforms with 33-minute turnarounds. Now, that means trains spend more than half an hour in the platform, which means a very large station. If we have a lean operations plan, if we reduce the time to 30 minutes, we can lose one platform. If we can get it down to 12 minutes, we have only 5 platforms. So If it's 6, we've already got some reserve. So Daisuke, as the last piece of his research, looked at the Taguchi analysis of the different factors which affect the turnaround performance. So he looked at 4 different layouts. He looked at a number of different signaling systems with shorter headways, and he looked at where the points and so on were. And what he discovered was that the signals have the greatest influence on the system in order to make the system work. Now, this is not something which we have designed, but the layout for the Houston HS2 station as planned at the moment includes a dive under so that you can change between the 2 sides of the station without conflicting movements. The gray area, the grayed out area of the station is for phase 2. Phase 1 has got a very much smaller layout. Now you might imagine that if lean principles are applied to this station, we might actually be able to forget about the phase 2 expansion and still turn around 17 or 18 trains. So, okay, does anybody actually apply the Japanese approach outside Japan? Yes, the plans for the Singapore to KL railway, or to be politically correct, KL to Singapore railway, are based on a Shinkansen approach with a large number of stations, which will still allow them to reduce the journey time, but it's a development tool for that whole sector of Malaysia. It will have 8 stops over 350 kilometers, so very similar to the Tokyo to Osaka high-speed line. And this is just an overview of what it will mean. I think the greatest benefit will be the reduction in flights and the reduction in car travel, because there's an enormous level of pollution just outside Singapore and actually in Singapore and KL because of the airports. So what I found when I visited Japan was that there's a focus on simplicity rather than complexity. It improves the control of resources and performance, which then gives you a much higher process predictability, so you can turn around trains in 12 minutes. It gives better outcomes for the customers. It makes operational resources allocation better. Everybody who's involved in the system is much more motivated because they've got achievable targets and they've got very measurable success criteria. It's not about buying tools, it's about talking to people, making changes that at all levels of management produce continuous improvement of processes. So that's the presentation. Thank you very much, and I look forward to critical questions.
Outstanding, Felix, and thank you for that thoroughly interesting talk. Just a reminder to everybody on the call, if you do want to ask a question, there's a chat facility up at the top right of the web window, and you can just pop into there and ask a chat question. That will come directly to me, and I'll ask them in the order that they've been presented. A question I've been asked by several people is, will the recording of the talk be available? So this will be made available at a later date on the PWI website, so keep your eyes out for that one. The first technical question comes from Richard Marsh, and that one is, how does the infrastructure owner maintain the fine tolerance required for high speed in a seismic area?
So it's for the Tokyo Shinkansen is mostly on ballasted track, and there is a lot of maintenance during every night in order to maintain the track in the right position. It's heavy rails, it's heavy sleepers, so that keeps it in one place, and it's deliberate that it's ballasted track in case there is an earthquake which moves things, then you have to adjust it, and that can be done very quickly.
Okay, thank you.
I think it's an important point is that the line is divided into lots of different sections, and each section does the work for its own area. And before they hand over the train back to service, there's a sweeping train going through at about 100 kilometers per hour to check that everything is fine.
Okay. The second question comes from Jonathan Harris, and that one is, what do you consider the optimal balance between axle weight with more powered axles and cost of infrastructure such as bridges and wear and tear on the track?
Well, the axle loads are actually not that big. So if you think you've got 730 tons and it's 64 axles, so the wheel load is roughly something like 6 or 7 tons. Building the trains light helps.
Okay. And then another question from Richard Marsh. Does Felix have any idea why there are two different approaches between Japan and Europe? For example, HS2 set out to have the fastest railway in the world at 400 kilometers per hour. To what benefit will this be in our small country?
Don't ask me that question because my answer is not very politically correct. The country is too small for 360 kilometers per hour unless you go to Glasgow and Edinburgh.
Okay, thank you. And then another question. Do Japanese infrastructure projects have the equivalent of a hybrid bill and environmental impact studies?
Yes, they have very serious environmental impact studies. The process takes a fair amount of time. It's very rigorous, particularly for noise. And one of the reasons why having lots of stations is a good thing is that if you are have a station in your small town, you're going to be less bothered about the trains coming through on a viaduct because it gives you much better mobility.
Okay,
so that's a big benefit, and it means people are happier about it.
Thank you. And the next question is from Phil Holborn. For the smaller S&C, do they use much higher rates of change of deficiency than we do?
You mean the deficiency, cant deficiency?
Yes.
No, it's very similar to here.
Okay. And then another question from Julian Heathcote. Oh, sorry, that's a copy of the slides. So yeah, so the slides will be made available along with the recording on the PWI website at a later point. And then another question from Ian Dean. How is maintenance conducted in 4 to 5 hours?
Well, ballasted track is beneficial in that respect, and having very short points is extremely beneficial because you can swap one out in the 5 hours you have got available. You don't, and that's actually quite similar to some other work I've come across in Switzerland where points are kept relatively short in order to have rapid exchange.
Okay, thank you. And the next question is from Judith. Do you have any views on ballasted track versus slab track? How do the initial costs compare, and what do HS2 propose?
Slab track is more expensive at first cost, and all the information I've got indicates that ballasted track is more expensive in the long run because of the maintenance and renewals. The question really is also about the resilience of slab track and ballasted track. If you look at the German situation where there was a washout underneath a section of slab track, that stopped the railway, the high-speed railway, for several months. With a ballasted track, you can fix something like that very quickly. And so in Japan, a lot of stations have got slab tracks, and some of the newer lines have got slab tracks, but they are very carefully designed with earthquakes in mind.
Okay, thank you. And the next question's from Mary Wells, who's interested in the correlation between braking and acceleration and rail wear.
There is an issue of rail wear now, because all the axles are, or rather most of the axles are electrically braked. Then wheel slip, wheel slide can be controlled better. It makes life a lot easier in that respect. But of course, the acceleration areas and braking areas are more heavily used. But using electric braking, electric acceleration gives you more, and of many axles, gives you lower track forces in those areas. So if you think that you've got 5-ton wheel loads, that makes a lot of difference.
Okay, thank you. And the next question is from Mike De Silva. On the surface of it, there are no negatives compared to the European approach. What are the benefits in the European approach?
I mean, I was explaining that you can gain about 7 seconds between a stopping train and a passing train. So if you translate that into an hour with 20 trains, that's 140 seconds. So that gives you nearly 2.5 minutes of extra time, but it's probably not that relevant, because at 17 trains per hour you have got more than 3 minutes between trains anyway. So having an extra 2 minutes in an hour is probably not that beneficial. I think the Japanese approach has got many, many advantages and relatively few drawbacks.
Okay, thank you. The next question's from Steve Featherstone. How important is it that the operation of track and train have a joined up total systems approach?
It is beneficial. It's always been that case for the Shinkansen system, is that the track and the train is run by the same people. The infrastructure is owned by Central Japan Railway. It's maintained by them. But I think it's a coordination question, and with goodwill, I think it works with contracts as well. And I mean, they have got trains from Central Japan going down to Hiroshima on West Japan, and you've got trains from West Japan coming into Tokyo. So collaboration is the key here.
Okay. And the next question is from Anthony Marquez. Given the existing plans for phase 1 and the government's interest in reducing the cost of phase 2, is it feasible to have a lean approach for phase 2, or will the proposed phase 1 infrastructure prevent implementation of this?
Well, certainly the infrastructure at the planned infrastructure at Euston and the intermediate infrastructure at Old Common can both be operated with a lean approach, and they will it will be beneficial. I think there was a question about Crewe having being built originally with very short turnouts, because it was expected that all the trains stop at Crewe. And so going further on towards the north, phase 2, if the captive trains have got higher performance than the trains which are used on the conventional network, then there may be some benefits of changing some of the approaches.
Thank you for that. Yes, that does cover one of the next questions as well. So the next question I've got here is from Irfan Khan. Has the reduction in infrastructure costs been quantified due to the restriction in speed, also taking into account noise issues and cracking on track slabs or tamping in ballasted track? I think he later goes on to quantify that this means between 360 and 300 kilometers per hour.
No, that has not been quantified, but I think many of these things go up by the square of the speed. So energy use goes up by the square of the speed. Track damage, I think, does to some extent, but I'm not an expert in that.
Okay, and the next question from Tin Seng Tai, I hope I've pronounced that correctly. Felix, will you be doing a similar study for high-speed rail in China in the near future?
I'm not going to do that, but I'm hoping that we might get a PhD student to do it. The Chinese high-speed rail system has been very significantly designed according to Western principles. So if you look at some of the high-speed rail stations in China, they're absolutely huge, and they are to some extent prestige projects rather than actually representing, showing what is required. Beijing South Station, Hangzhou Station, they are much bigger than they actually need to be. So prestige is an important issue in building high-speed rail.
Okay, and the next question from Phil Holborn. Are the rail types and wheel profiles similar or the same, or do they have very different profiles?
To my knowledge, they are very similar.
Okay. And then a question from Andy Cooper. Does the massive amount of nuclear electricity in Japan make it easier to pay a bit less attention to the energy use?
Well, actually, they pay more attention to the energy use, because if you can regen from 300 kilometers per hour down to 20 or 30 kilometers per hour, you save a hell of a lot of energy, and therefore stopping is not such a penalty. Whereas if we stop largely on the mechanical brakes down to about 150 kilometers per hour, then that energy is gone. It's gone away, no longer there. So okay. I think the source of energy is important, but the Japanese try to pay as little as possible for the electricity.
Okay. And the next question from Kevin Thurlow. What is the impact of a mixed traffic railway on the process with the need to have unused paths and keep different kind of trains apart? Or is there only one or a limited type of stock used?
On the Shinkansen system in Japan, the decision to go for standard gauge when the national network, which is freight, suburban, and interurban, is done on Cape gauge. So 1067 millimeters means that there is no demand for slower trains or different trains on the Shinkansen network. So the only difference is when you introduce a new, more powerful type of Shinkansen train, there is a period during which the old trains are still running, and therefore the timetable has to be slightly relaxed.
Okay, thank you. And a question from Jonathan Harris. In general, how do Japanese railway operational practices and rules differ from those in the UK?
The rules are fairly similar, but the way in which staff are developed is very different. So you start out as station staff or cleaning staff. Even if you're a degree level person, you then move into conductor grade, you move into driver grade if you're suitable for it. And then after a period as a driver, you may well go back to become a station master or to become a trainer. So once you're in a job, doesn't mean that you're there for life. So there are opportunities to changing in and out. And most of the operation of the managerial staff can actually drive trains.
Okay, and then a question from David Holmes. It would appear that in Japan, station accurate dwell time is critical. How is this done reliably?
It's training the passengers really, and the staff are very particular about how they manage things. And we all have seen people pointing at clocks, people pointing at the train, but that's the staff really are focused on getting the time absolutely spot on and whistling at people in order to get on the train. So it is a very strong focus.
Okay, and a question from Tinseng Tai. Is it feasible to have high-speed rail operating together with higher speed trains, so 300 kilometres an hour versus 160 kilometres an hour on the same track in order to reduce the numbers of stops on high-speed rail and thus reduce the journey times?
Well, I think what the Japanese approach says that all the trains are the same. All the trains can brake very rapidly. So a Nozomi train, which is a slower train than a Hikari, that train will get to the same top speed as a Hikari and will brake hard into the stations. So it's not two different speed levels, because having two different speed levels really kills your capacity. So 160 kilometer per hour train between 300 per hour ones loses you a huge amount of capacity on the infrastructure.
Okay, and I think we've got time for two more of the questions on here, and then we'll probably look to draw to a close. So the next one's from Ian Dean. Is the track position maintained rather than allowing floating geometry?
Well, to achieve the speeds which are achieved, you really have to keep the track very closely to its design position. So that's why there is a lot of tamping and a lot of work going on to keep the track in the same place.
Okay, and then if we do this as a final question from the chat, and then I might ask Kate to open the lines up just to see if anybody's got anything else. So this question's from Taleb Kamazi. How much of the benefit of the Japanese approach has been fed in or incorporated into HS2?
I think relatively little. I don't know why, but I think that the objective of running faster than any other railway in the world was probably a factor in saying, oh, the Japanese only do 300, so their knowledge is perhaps not that useful. But that's pure conjecture. That's not something which I can document or which I would actually say as an important point.
Okay, so just before we open the lines of the people who've dialed in, just to let everybody have a chance to ask any questions they might have, just a couple of final things from me. Firstly, thank you, Felix, very much for a really interesting talk. I think at peak we got up to about 201 people on the line, so you've had a really good attendance, and I'm sure we've all found it as interesting as I did. One final thing to mention is that the PWI starting next week, and the details and the booking details are all on the website, are running some special online talks, some spalks. The first one's on, yeah, that's the slide there from Kate, thank you. So first one on Monday the 18th of May, which is on supporting the industry physically and mentally through the COVID-19 emergency. I know Nick Millington's spoken before on one of these online talks, and I found him excellent personally, and he's I could highly recommend him, and Jones obviously always good value for money for myself as well. So highly recommend you dial into that. I know I will be, and that's at the same time as this, with the talk starting at 1:45, so runs nicely over lunchtime. Kate, if you want to open or Sarah, if it's Sarah, open the lines up to see if anyone's got any final questions.
Yep, I have opened it. We've only got one person that's dialed in today, so we'll see if they've got a question.
Okay, so we'll draw it to a close there to get it finished for 2 o'clock as scheduled. Thank you all very much for attending today, and I look forward to virtually seeing you at one of these in the future. Thank you.
Thank you so much,
everybody.
Thanks. Awesome.